So if I entered in all that data and I hit submit, told me my slope and intercept and regression line, and we see the scatter plot. We go down here, we can hit that correlation coefficient. And of course, it has to give me an add. So if we go back here, what we find is that my correlation coefficient is roughly 0.956. That your regression equation, so remember it's a y hat here, is roughly 3.19. We'll round to three places here just for us. And if you notice, I said the x after that first data point, then you have the minus, and then we have the 42.785. So always be careful when you look at these regression equations. Is that sometimes where the x shows up, it's either like the first data point, it's the second one, but you always have to be careful, watch out where that is. So sometimes it might be easier just to go based off of the intercept and your slope and use those instead. So we'll bring those points here back in a second. So what we had said is that my correlation coefficient was 0.956. So it's a very strong relationship. And my equation was 3.192x minus 785. So what is our linear relationship? Well, I see that we have a positive slope. So it is a positive relationship. Means it's increasing. Strength of relationship, we would say it's strong because our correlation coefficient is really good. Now, if we figured out our coefficient of determination, so what percentage of the change in murder rates is predicted by changes in the percentage of families in poverty? So as we said, we need our coefficient of determination. Which is our R squared. So that's going to be my 0.956 squared. And if I square that, I end up with 0.914 if we round it. So what I'd say here is that 91.4% of changes in murder rates are predicted by my percentage of families in poverty. Or we are going to say they're predicted by poverty rates. So I believe that was real data that I had used there. I can't remember where I got it from. But this is actually a common thing that you see is that poverty is a good predictor of crimes and violence. In this case, it's a really good predictor because 91% of our changes that we see in murder rates can totally be predicted by our poverty rates. All right, so a little bit more. So using linear regression equation, we want to answer the following. So I just put the equation back in the corner there. what does the slope of the equation tell us about the relationship between poverty and murder rates? So slope is, oops. So if you remember, murder rates were in number of murders in 1,000 people. So we gain 3.192 murders per million people. If the poverty level, which is my X value, if it increases by 1%. Because we talked about our poverty levels in percents. So just kind of talking about what this data is telling me. So every time my poverty level increases by 1%, there's going to be roughly 3 more murders per 1,000 people. What does the y-intercept tell us about the relationship about poverty and murder rates? Well, it's telling me that this is something useless. If the poverty rate is 0, we have negative 42.785 murders. Per 1,000 people. Or sorry, not 1,000, 1,000,000 people. So in this case, it doesn't tell me anything because that's a ridiculous thing. We can't have negative murder rates. So slope usually tells us something that's useful. Y-intercepts don't always do that. What that's probably telling me is that there's sort of like maybe a baseline of like murder rates you expect to see. And that we have something that's at some point doesn't stay linear. And that happens a lot. Like part of our models are linear, but when we start getting close to the edges, like if we got to 100% poverty rates or 0% poverty rates, things start acting weird. So if 20% of the families have an annual income under 5,000, what is the murder rate? So really what I said here is that my X is 20. So if 20% of my families are in the poverty level, which is really what it was telling us here, we just stick that in here. So we end up with 3.192 times 20 minus 42.785. We're going to have approximately 21.055 murders per million people. So just something to show you back here with this equation, or this calculator here. Actually, you can type in an X value, so I could have typed it in here and calculated it. And we get something that's pretty close. So we had 21.055, we get 21.050. So really, really close. So the last thing we have to talk about are influential outliers. So sometimes an outlier has a strong effect on the regression equation and possibly reducing the predictability of the equation. If removal of the outlier causes a significant change in the regression equation, it's considered an influential outlier. So what we have here is our Verizon data. Not Verizon data. I'm sorry, it's our Orion data. We haven't used the Verizon data in forever. And most of my data was clustered kind of in this little area here. And we have this one data point that's far away. So that's an outlier that we have. The question is it an influential outlier? So what we have here is that if I keep all my data, we had saw this last time, that my regression equation was this, was a, I'm sorry, 195.47 minus 20.26x. That's what we found last time that we had dealt with this Orion data. So that is if I keep the outlier. If, however, I remove the outlier, which is what I do down here, so influential observation removed from data, or possibly influential. And this is where things get a little tricky sometimes based on your equation. So here we remove outlier. We get a little different equation. So this one's saying that my cars start at a price of $19,547 is the price of a new Orion. This one's telling me is that if I have a new car, it's actually worth $16,133, which we know already is not correct because this is the price of a new car and that's way below it. Also, we see that there's a change in the slope. So here I am going to lose. Oops, put my come on the wrong pace. I am going to lose $2,026 per year in value. Here, I'm going to lose $1,424 per year. Sorry, my year didn't make it here. So what we see here is that the slope has changed by $600. So we're saying that without that outlier in there, that what I'm saying is the loss in value of my car has changed by $600. We also see, like I said, that the y-intercept is changed by quite a bit as well. We're saying that the car is now $3,500 cheaper without that influential outlier. That's enough to say that that outlier is influential. So without the influential outlier, or without the outlier, the equation modeling the value of a Orion changes a lot. So because we have a lot of change, we say the outlier is influential. And the reason that we care about this is sometimes we might decide to remove this outlier because we might think it's making too big of a change to our data. Or sometimes we decide we need to keep it because maybe it's keeping things where it should be. But like I said, it's telling me that this outlier has influence in my data, and I would have to do more analysis to decide if I actually want to keep that outlier. So sometimes we do decide to remove outliers from data, and if I did that, I'd be more focusing in on this data here in the center. So in that case, it might not be a good idea to remove it because then I only have this data to work on. But it's also telling me that maybe only this part acts linear and maybe this part is not linear. It's something's changing in the way the data behaves. So just telling me that the outlier has some sort of influence, and I need to look into that a little bit more. So take a second and work this with poverty rates. So what we're going to do is I want you to look at this data and see if you can identify a outlier and then determine whether you think it's influential or not. So I'd pause right now, take a few minutes, look at it, and then we'll go back and analyze this. So if you look at this data, I think we could pretty easily determine or decide that this data point is really far removed from the rest, and this is probably your outlier. So this outlier would have to be the data point, just a second, I gotta find it here, 26.3 in your data, and then we had 40.7 murders per million people. So if we kept that outlier in here, we already found out we get this line of y hat equals 3.192x minus 42.784. So what I want to see is if I remove that outlier, what do I get? So without the outlier, like I said, it would have to be this data point here. We're just going to remove it and we're going to submit the data again. So might as well get rid of this because my outlier is gone. And now my new equation is this. So as you see, slope hasn't changed a whole lot. So we want to having maybe 3.2 people murdered every time the poverty rate goes up by percent to 3.6 people. That's not a big difference. So slope has changed little. If you were to still round this, we're increasing by roughly like 3 or 4 people. It's not a huge difference here. If you look at your y-intercept's not a big difference either. It's saying that initially I started at 42, and the other one is like I started, well, 43 and then 50. So not a huge change again. Slope has little change. Intercept has little change. In that case, what we'd say is that this is not an influential outlier. Still maybe an outlier, it's just not influential. It means we don't have to really think about it a whole lot. It's not, having it in there is not making a big difference to my data. What we're saying is we don't have something that's, it's an outlier that's not really weird. So it's probably, we are seeing a linear change in the data. That's one of the things it's telling me, because if I remove that outlier, I don't have a big change in my equation. It's also telling me that it's not a really bizarre data point. It's just I happen to have one time where the poverty rate was particularly high in an area. But overall, the model stays the same. So in this case, it's not an influential outlier.